All right, let's dive into one of the most fascinating and famously tricky problems in all of computer science. How in the world do you get a bunch of computers to agree on anything, especially when everything is going wrong? We're going to break down the legendary algorithm built to solve this exact problem, Paxos.
I mean, really think about that for a second. You've got all these different machines, and they need to land on one single consistent answer. But what happens when messages get lost in the ether? What if a server just, poof, vanishes right in the middle of a critical vote? How do you stop the whole system from descending into complete and utter chaos? Well, that's the very question Paxos was designed to answer.
So here's our game plan for today. We'll start by digging into why agreement is such a tough nut to crack. Then we'll meet the key players in the Paxos world. After that, we'll walk through its core two-phase handshake, explore what it guarantees, see where it's used in real life, and I'll leave you with a final thought to chew on. Let's do this.
First things first, let's be super clear about why this matters so much. Getting a group of machines to agree isn't just some nice-to-have feature. Nope, it is the absolute bedrock of any distributed system that you want to be reliable.
Just picture it. Every computer is basically its own little island. They can't just look at some shared whiteboard. There's no shared memory. There's no master clock they can all sync their watches to. Any one of them could crash at any second, and any message they send might just disappear into the void. And yet, through all of that mess, the system absolutely must not come up with conflicting answers. That would be a disaster.
Okay, to make sense of how Paxos works its magic, it really helps to think of it like a stage play with three main characters. So, let's meet the cast.
First up, we have the proposer. This is any machine in the system that has an idea it wants everyone to agree on. It's the one that kicks the whole process off by suggesting a value. Maybe something like, let's commit this database transaction, or hey, let's make this server the new leader.
Next are the acceptors. You can think of these as the judges, or the jury, or maybe the voters in an election. This group's entire job is to listen to the proposers and cast their votes. The actual decision gets hammered out right here, among the acceptors.
And finally, we have the learners. Their job is pretty straightforward. Once the acceptors have made a final decision, the learners just need to find out what that decision was. It's worth noting that in a lot of real-world systems, one computer can actually wear all of these hats at the same time.
So, you've got the players. How do they actually reach an agreement? Well, it all comes down to this really clever two-phase protocol. Now, I know it sounds intimidating, but honestly, it's best to just think of it as a two-act play.
The whole dance breaks down into two main phases. Phase 1 is all about getting permission to even make a suggestion in the first place, and Phase 2 is where the group actually reaches an agreement on a specific value. That's it. Permission, then agreement.
So it all begins with a proposer. It picks a proposal number, n, and this is super important. That number has to be higher than any number it's ever used before. It then sends out a prepare message with this number to a bunch of the acceptors. It's basically saying, hey everyone, I'd like to make a proposal, and my ticket number is n. May I have the floor?
An acceptor gets this message and checks the number. If n is higher than any other proposal number it's seen so far, it makes a critical promise. It replies, saying something like, okay, your number looks fresh. I promise I won't listen to any proposals that have an older, smaller number. And then it sends that promise back to the proposer.
So why all this ceremony? Well, this step is absolutely key for creating order. It acts like a filter, making sure that old, delayed messages that might be floating around the network can't show up late and cause confusion. Only the proposal with the newest, highest number gets to proceed.
So once our proposer has heard back from a majority of the acceptors, it knows it has their blessing. It has permission to proceed. Now, and only now, it sends out its real proposal, an accept request. This message contains that same proposal number n, but this time it also has the actual value it wants everyone to agree on.
An acceptor gets this second message, and because it already promised it would listen to proposals with the number n, it has to keep its word. It formally accepts the value and lets the learners know what the final decision is.
And that right there, that's the moment of consensus. As soon as a majority of acceptors have accepted that value, it's locked in. It becomes the single, indisputable truth across the entire system. The decision is made, it's final.
So what's the deal with that magic number, the majority? Well, it's based on a simple but brilliant mathematical truth. Any two groups that are both a majority must overlap. They have to share at least one member. And it's that overlap that makes it physically impossible for the system to choose two different values. It's what prevents the dreaded split brain scenario.
So we have a way to reach agreement. Awesome. But what does Paxos actually guarantee? And what are the hidden costs? Because like with anything in engineering, it's all about the trade-offs.
Okay, Paxos gives you two fundamental promises. The first and the most important one is safety. This means the system will never agree on two conflicting things, ever. That is its top priority. The second promise is liveness, which means the system will eventually choose a value. And notice that word, eventually. In a worst-case scenario where two proposers get stuck in a duel, constantly one-upping each other's numbers, the system can stall. But in any normal situation, it will always make progress.
But those amazing guarantees don't come for free. Paxos is, well, chatty. It involves a lot of back-and-forth messages, which adds latency. And maybe most famously, it is notoriously difficult to implement correctly. I mean, it's a beast. So while it's incredibly powerful, it is definitely not a simple solution.
So you might be thinking, if this thing is so complicated, who on earth actually uses it? Well, it turns out its core principles are humming away behind the scenes, powering some of the most critical systems on the entire internet.
Google's famous Chubby lock service, which was a cornerstone of their infrastructure, Paxos. A lot of the internal coordination systems at places like Amazon, you guessed it, they use ideas directly from Paxos. And pretty much every major distributed database uses Paxos or a variant of it to keep data in sync and to elect a leader. Even modern, supposedly simpler algorithms like Raft are really just direct descendants built on the groundbreaking ideas that Paxos introduced first.
Okay, let's bring this all together. Understanding Paxos isn't just some abstract academic exercise. It's really about understanding a fundamental choice that every systems designer has to face.
At the end of the day, Paxos represents a really clear trade-off. It chooses absolute mathematical correctness, that is safety, over things like simplicity and raw speed. So the real question for any engineer is, when is that the right call? When is the cost of being wrong so astronomically high that you are willing to pay the complexity price for this incredibly powerful algorithm? Something to think about. Thanks so much for tuning in.